Okay, so we start out here with section 18.3, and we get back into our equilibrium expression, which I just want to start out with a couple of reminders of our equilibrium expression. Number one, we have to remember that products are going to be divided by the reactants, products over reactants. Key there. The second key thing is that we can only have gases and aqueous solutions in our equilibrium expression. Solids and liquids are not in that equilibrium expression. And then the last thing that I want to remind you is, what does K mean? All right, so we have a really big K, and when I say really big K, I mean more than one. Your products are going to be favored. So there's going to be a higher or greater concentration of our products at equilibrium than reactants. And then if we have a small k, our reactants are going to be favored. And so there is more or a higher concentration of our reactants than products in this case at equilibrium. Okay. Now, K is always going to be a positive number, so the small k will be between 0 and then less than 1. Okay. Remember, we can do a lot of calculations with our equilibrium, and that's what we're going to take a look into today and actually analyze and understand that a little bit more. All right, so now we found K when we are given the equilibrium concentration of every substance that's involved in the equilibrium expression. However, sometimes we are not given all the concentrations, but we know K. And all of this is derived from calculations that are done from lab experiments. And so what we're going to do today, we're going to do something very similar. We're going to set up our equilibrium expression, and we're going to figure out what we know and don't know, and then solve for that unknown variable. Okay, so let's go ahead. Let's try one example here of this. All right, so we have a temperature that says at 1,405 Kelvin, that's our temperature, hydrogen sulfide, also called rotten egg gas because of its bad odor, decomposes to form hydrogen and a diatomic sulfur molecule, S2. The equilibrium constant, so our K, for the reaction is 2.27 times 10 to the negative third. We want to know what is the concentration of hydrogen gas if the concentration of sulfur is 0.0540 molar and hydrogen sulfide gas is 0.184 molar. Okay, so the first thing that we always need to do when we get to an equilibrium expression is actually write our equilibrium expression without numbers. Okay, so we're going to start out with this. I am going to simply write the equilibrium expression for what we have here. And so we always start out with K, and we put EQ again to remind us that we are at equilibrium, right? But we do need a big K out in front. And then we're going to put our products on top. Now, first product that we get to is hydrogen, H2 gas. And remember, we have to raise that particular substance to its coefficient. So we're going to raise it to the second power. So it'd be H2 squared times S2. Now, if we look really, really closely, S2, there's nothing written, so we assume a coefficient of 1. And so that would be what's on top. Now, we divide this by our substance that is our reactant, which is H2S. Now, just as a reminder here that this business up top would be times, okay? The other thing I should have pointed out is that all of these substances in this particular equilibrium expression are gases, so that means every single one of those items are included in our equilibrium expression. Remember, gases and aqueous substances are the only items that can be involved in our equilibrium expression. All right. Now let's go back and let's figure out what we have. Okay. And so I'm going to use some different colors here. And I'm going to start up here. Up here it says the equilibrium constant is 2.27 times 10 to the negative third. Well, remember, the equilibrium constant is our KEQ. So we're going to go ahead and just to the right here, I'm going to write our equilibrium constant to be 2.27 times 10 to the negative third. Remember, there's no unit. And this is equal to our hydrogen gas. Now, our hydrogen gas here is what we are trying to solve for. It says, hey, what is hydrogen gas? So that's our unknown, that's our X here. And so we would have our H2 gas. Now, really important, we can't forget about that expression. And sometimes I view this almost as a formula. It is actually squared, okay? Now, we keep moving on here. I'm going to use a different color. And we are going to talk about, okay, now our sulfur, S2, is given at 0.054, okay? And so 0.054 is what we're going to say, hey, times our 0.0540, and technically this would be moles per liter is molarity. All right. Now, all of this would get divided by our particular product, which has a concentration, our H2S, or excuse me, our reactant, 0.184 big capital M. And so now we have our setup to be able to solve our problem. So the first thing that I'm going to do is I'm going to cross multiply my K and my 0.184. Okay, so I'm going to take this and I'm going to say, all right, 2.27 times 10 to the negative third times 0.184, and I get a value, I'm going to use scientific notation here, of 4.18 times 10 to the negative 4. Okay, so when I multiply these things together, I get 4.18 times 10 to the negative 4. This is all equal to our hydrogen gas, which is squared, H2, that is squared. And then we multiply this by our given value here for our given value for our H2S. Which is 0.0540. Okay. Now we got to get H2 squared all by itself, so we're going to divide each side by that 0.0540 moles here, or excuse me, molar, and we'll do this on both sides. So when we do this, I'm actually going to keep the number in my calculator, and I'm going to divide this by 0.054. I get a value for H2 squared. I'm going to write it out to the left to be 7.73 times 10 to the negative third. So we get, again, 7.73 times 10 to the negative third. this is all equal to our hydrogen gas that is squared. So we got to do one more mathematical step here, and we got to get rid of that squared so we can solely find our concentration of hydrogen. So the way we do that is we just take the square root of each side, okay? So we take the square root of what we got here, and so what we'll do is we'll take the square root of that number, and we get a concentration, an H2 concentration, to be 8.79 times 10 to the negative second. And that would be in units of big capital M for molar. Now, that's the same unit as moles per liter, okay? So the key thing here is this, just like we've seen before, you got to set up your equilibrium expression. That's that item we wrote here in black. And then you can solve for what you want. You kind of plug that into what I like to call our formula, all right? So we're gonna stop here for right now. This is a good stopping portion for section number 3.